You think black holes are holes, giant cosmic drains sucking everything into nothingness, dark empty spaces in the universe, where matter disappears forever. But what if I told you that black holes aren't holes at all? What if everything you think you know about these cosmic monsters is wrong? What if black holes aren't destroyers, but creators? What if they don't erase information, but preserve it? What if the inside of a black hole doesn't exist the way you imagine? And what if falling into one doesn't kill you the way you think it does? Let me show you what's really inside a black hole, and I promise you the answer will change everything you think you know about reality itself. First, let's destroy the most basic misconception. Black holes are not holes, they're not empty spaces, they're not cosmic vacuum cleaners. They're objects, incredibly dense, incredibly massive objects with surfaces, real physical surfaces. We call this surface the event horizon. It's not a magical barrier. It's not a portal to another dimension. It's simply the boundary, where the gravitational pull becomes so strong that nothing, not even light, can escape. But here's what your intuition gets wrong. When you imagine falling toward a black hole, you picture plunging through empty space toward some dark center, but that's not what happens. You fall toward a surface, a real physical boundary. The event horizon is where the black hole actually is. Everything inside that boundary is the black hole, solid, dense, real. Think of it this way: the Earth has a surface. You can dig through the entire planet and come out the other side passing through empty space. The Earth is full of matter all the way through. A black hole is similar, except instead of rock and metal, it's made of space-time itself, curved so extremely that it closes in on itself. Now here's where things get strange. What happens when you fall toward this surface? From your perspective, falling in, you approach the event horizon normally. You don't feel anything special happening. You don't notice crossing some cosmic boundary. To you, you simply fall through what seems like empty space. But here's the thing that will break your brain. You never actually reach the surface. Not from your own perspective. This seems impossible, so let me explain. As you fall toward the black hole, your time dilates. It runs slower and slower relative to the outside universe. Near the event horizon, time dilation becomes extreme. From your perspective, time passes normally. Your watch ticks at its regular rate. But relative to someone watching from far away, your time slows to a crawl. Now here's the key insight. The extreme time dilation means that from your perspective, you experience the entire future history of the universe compressed into the time it takes you to reach the event horizon. You see galaxies form and die. You see stars burn out. You see the universe expand and cool. All of this happens while you're still falling, still approaching but never quite reaching the surface. But what does someone outside the black hole see? They see something very different. From their perspective, as you fall toward the event horizon, you slow down. Your image becomes redder and dimmer, as time dilation stretches the light waves coming from you. Eventually your image freezes at the event horizon, fading away as the light becomes too stretched to detect. To them you never cross the boundary. You remain frozen there forever. So which perspective is correct? Both. This is the relativity of experience. There is no universal viewpoint, no God's eye view that shows what really happens. Reality is what you experience, and different observers experience different realities. You experience crossing the event horizon and falling toward the center. The outside observer experiences you never crossing at all. But let's continue with your journey inward. You've crossed the event horizon from your own perspective. What do you find inside? This is where most people's imagination fails completely. They picture empty space leading to some kind of central point, a singularity where all the mass is concentrated. But this picture is wrong. Here's what you actually encounter. As you fall deeper inside the event horizon, space-time becomes more and more curved. Not just curved in the sense that gravity is strong, but curved in ways that challenge the very notion of space and time as separate things. Inside a black hole, the direction toward the center becomes time-like, not space-like. This means that falling toward the center is more like moving forward in time than moving through space. Think about this carefully. Outside the black hole, you can choose to move left or right, forward or backward, through space, but you cannot choose to move backward, through time. Time has a direction, and you're carried along, whether you want to be or not. Inside the black hole, the center becomes like the future. You can't avoid moving toward it any more than you can avoid moving forward, through time. The center of the black hole is not a place you arrive at. It's a moment that you experience. But what is that moment like? What happens at the center? This is where we encounter the concept of a singularity. A point where density becomes infinite, where space-time curvature becomes infinite, where the laws of physics as we understand them break down completely. Most people imagine this as a tiny point of incredible mass, but this too is wrong. A singularity is not a thing. It's not an object. It's not even a place. A singularity is a moment. A moment when the geometry of space-time becomes so warped that the concept of location stops making sense. It's like asking what's north of the North Pole. The question itself doesn't make sense, because you've reached the limit of the coordinate system. Now let's add quantum mechanics to this picture, and this is where everything gets truly strange. When we apply quantum mechanics to black holes, we discover something shocking. Black holes are not perfectly black. They radiate energy. They glow with thermal radiation. This is called Hawking radiation, and its discovery completely changed our understanding of what black holes are. Here's how it works. Empty space is not actually empty. It's filled with quantum fluctuations. Pairs of particles constantly appearing and disappearing. Usually these particles annihilate each other so quickly that we can't detect them. But near the event horizon of a black hole, something remarkable happens. One particle from a pair might fall into the black hole, while the other escapes. The escaping particle becomes real Hawking radiation. This means black holes slowly evaporate. They lose mass by radiating energy. Smaller black holes radiate faster than larger ones. A black hole with the mass of our Sun would take longer than the age of the universe to evaporate completely, but a black hole the size of a proton would explode in a tiny fraction of a second, releasing the energy equivalent to millions of hydrogen bombs. But here's the disturbing part. The Hawking radiation appears to be completely random. It seems to carry no information about what fell into the black hole. If you throw a book into a black hole, the information in that book appears to be destroyed forever when the black hole finally evaporates. But quantum mechanics says information cannot be destroyed. This contradiction is called the information paradox. For decades this paradox tormented physicists. How can information be both preserved, as quantum mechanics requires, and destroyed as black hole evaporation seems to imply? The answer, when it finally came, was more radical than anyone expected. The information isn't destroyed, it's encoded on the surface of the black hole, on the event horizon itself. This leads to one of the most mind-bending ideas in all of physics, the holographic principle. Everything that happens inside a three-dimensional black hole can be completely described by information encoded on its two-dimensional surface. The volume is an illusion. All the information, all the complexity, all the detail of everything that ever fell into the black hole is written on the boundary. Think about this carefully. You fall into a black hole. From your perspective, you experience a rich three-dimensional journey toward the center. You feel the increasing tidal forces. You see the geometry of space-time warping around you. You experience the approach to the singularity. All of this is real to you. But according to the holographic principle, all of this experience, all of this information, can be completely described by patterns on the two-dimensional event horizon. This suggests something profound about the nature of reality itself. If a three-dimensional volume can be completely encoded on a two-dimensional surface, then perhaps our own three-dimensional reality is similarly illusory. Perhaps we are living in a hologram. Perhaps the rich, detailed universe we experience is actually encoded on some distant two-dimensional boundary. But let's go deeper into what this means for the interior of black holes. If all the information is encoded on the surface, what does that tell us about what's inside? Some physicists argue that there is no inside, that the interior of a black hole doesn't exist as a physical space, that when you fall past the event horizon, you're not entering a three-dimensional volume, but rather becoming part of the information encoded on the boundary. Others argue that the interior does exist, but is somehow equivalent to or dual to the information on the boundary. Two different descriptions of the same reality, like how a cylinder can be described as a rectangle rolled up or as a circular base with height. Different descriptions, same object. This duality between interior and boundary leads to even stranger possibilities. Some theories suggest that black holes are connected to other regions of spacetime through wormholes, that falling into a black hole might deliver you not to a singularity, but to a distant part of the universe, or even to a different universe entirely. But here's where quantum mechanics makes things even more complex. The interior of a black hole, if it exists, cannot be observed from the outside. No information can escape from beyond the event horizon. This means that the interior exists in a quantum superposition. It's simultaneously all possible configurations, until someone falls in to observe it. The act of falling into the black hole doesn't just reveal what's inside, it creates what's inside. This is similar to Schrödinger's cat, but on a cosmic scale. The interior of a black hole is simultaneously every possible interior until observed. Your decision to fall in collapses this superposition into one specific reality. You don't discover what was already there. You create what comes into existence when you arrive. Now let's consider what this means for your experience of falling in. As you approach the event horizon, you're not just approaching a boundary in space. You're approaching a boundary between different versions of reality. The version where the interior exists, and the version where it doesn't. The version where you fall to a singularity, and the version where you become information on the surface. From your perspective, you experience one of these realities consistently. You fall through the event horizon, experience the interior, and approach the singularity. But from the outside perspective, you become frozen on the surface. Your information encoded in the Hawking radiation that eventually evaporates away. Both descriptions are complete and accurate. Neither is more true than the other. But here's what makes this truly mind-bending. If the holographic principle is correct, then your rich, three-dimensional experience of falling through the black hole interior is somehow equivalent to a pattern of information on the two-dimensional event horizon. Your thoughts, your sensations, your experience of space and time are all encoded as correlations in the surface data. This suggests that consciousness itself might be substrate independent, that the subjective experience of being you doesn't require a three-dimensional brain made of atoms. It only requires the right pattern of information, regardless of how that information is physically encoded. Your conscious experience of falling into a black hole could be equally real, whether implemented in a three-dimensional interior or as patterns on a two-dimensional holographic boundary. Now let's explore what happens at the singularity. If you do experience falling all the way to the center, what do you find there? The traditional answer is that space-time curvature becomes infinite, that tidal forces become infinite, that you're crushed out of existence in an instant. But quantum mechanics suggests something different might happen. Near the singularity, Quantum effects become dominant. The classical description of space-time breaks down. Some theories suggest that quantum effects prevent the formation of a true singularity, that instead of infinite curvature, you encounter something called a quantum bounce. The collapsing matter reaches a maximum density, and then bounces back, potentially creating a new expanding region of space-time. This leads to the possibility that black holes are not endpoints but transitions, that matter falling into a black hole doesn't get destroyed, but gets recycled into new space-time, possibly even new universes. Every black hole might be the seed of a new cosmos, expanding beyond our ability to observe or detect. But here's an even stranger possibility. Some theories suggest that the singularity is not a moment of destruction, but a moment of transformation. That the information that falls into a black hole gets reorganized, compressed, and potentially transmitted to other parts of the multiverse. The black hole becomes not a grave, but a cosmic reproductive organ, spreading complexity and information across reality. Now let's consider the firewall paradox. This recent theoretical problem suggests that the event horizon might not be the smooth invisible boundary we think it is. Instead, it might be a wall of high-energy radiation that would incinerate anyone trying to cross it. This conflicts with the equivalence principle, which says that freely falling observers shouldn't experience anything special at the event horizon. The firewall paradox arises from trying to reconcile quantum mechanics with general relativity and the holographic principle. If information is encoded on the boundary, if Hawking radiation carries away information, if the interior is dual to the boundary, then the event horizon cannot be both smooth and information preserving. Something has to give. Some physicists argue that firewalls are real, that the event horizon is a genuine physical barrier that destroys anything trying to cross it. Others argue that firewalls are impossible, that they would violate fundamental principles of relativity. Still others suggest that firewalls exist, but only for observers who possess complete information about the Hawking radiation. For typical observers, the event horizon remains smooth. This debate reveals something profound about the nature of reality. There may not be a single objective answer to what's inside a black hole. The answer may depend on who's asking and how much they know. Reality at the quantum level may be fundamentally observer-dependent, not just in terms of measurement but in terms of existence itself. Let's explore another possibility. What if black holes are not isolated objects, but connected to the quantum structure of space-time itself? Some theories suggest that black holes are like nodes in a vast network of quantum entanglement that spans the entire universe, that information falling into any black hole becomes part of this cosmic web of connections. In this view, when you fall into a black hole, you don't disappear or get destroyed. You become part of a larger quantum system that includes every other black hole, every other particle, every other bit of information in the universe. Your individual identity might be lost, but your information becomes woven into the fundamental structure of reality itself. This connects to ideas about the multiverse and the anthropic principle. If black holes are connected through quantum entanglement, if information is preserved and recycled through cosmic evolution, then our universe might be just one node in an infinite network of interconnected realities. Black holes might be the mechanism by which information and complexity propagate across this multiverse. But let's bring this back to your direct experience. You're falling into a black hole. What do you actually feel? Surprisingly, for a large black hole like the one at the center of our galaxy, the experience might be quite gentle at first. The tidal forces near the event horizon are relatively weak. You wouldn't be stretched apart immediately. You might not even notice crossing the boundary. Only as you fall deeper toward the center, do the tidal forces become extreme. Your feet, being slightly closer to the center than your head, experience stronger gravity. You begin to stretch. This stretching accelerates as you approach the region where classical physics predicts a singularity. Eventually the stretching becomes violent enough to tear your body apart at the molecular level. But remember, this is only one perspective. From the holographic viewpoint, this entire experience is equivalent to your information being processed and encoded on the event horizon surface. The pain, the stretching, the final disintegration, all of this is a subjective experience that corresponds to objective patterns in the boundary data. This raises profound questions about the nature of suffering and existence. If your experience of being torn apart by tidal forces is equivalent to information processing on a distant surface, what does that mean about the reality of pain, about the nature of consciousness, about what it means to exist? Here's another mind-bending possibility. Some theories suggest that time runs differently near different parts of the event horizon, that the surface of a black hole experiences a kind of temporal complexity that doesn't exist in normal space-time. Different regions of the horizon might be connected to different moments in the black hole's history. This means that when you fall in, you might not just encounter the present state of the black hole. You might interact with information from everything that has ever fallen in before you. The event horizon becomes a kind of temporal nexus where all moments coexist simultaneously. Your fall becomes part of a timeless dance of information that includes every previous victim of the black hole's gravity. But here's what might be the most disturbing implication of all. If black holes preserve information through holographic encoding, if the interior experience is equivalent to surface patterns, if consciousness can be substrate independent, then everyone who has ever fallen into a black hole might still exist in some form, encoded in the radiation, frozen in the boundary information, experiencing their fall over and over again in an eternal quantum loop. This suggests a kind of cosmic immortality, not the comforting kind where you go to heaven, but a strange, quantum mechanical immortality, where your information pattern persists indefinitely. In the structure of space-time itself, you become part of the universe's memory, part of its information processing system, part of its attempt to understand itself. And if the holographic principle applies not just to black holes, but to our entire universe, then perhaps we are already living in such a system. Perhaps our three-dimensional reality is already encoded on some cosmic boundary. Perhaps we are already the preserved information patterns of beings who fell into some vast universe-sized black hole eons ago. This brings us full circle to the nature of reality itself. If black holes teach us anything, it's that the universe is stranger than we can imagine, that information and experience can exist in forms we never suspected, that the boundaries between inside and outside, between observer and observed, between real and encoded, are not as clear as we thought. So what's really inside a black hole? The answer depends on your perspective. From one viewpoint, there's a rich three-dimensional interior, leading to a singularity, where space-time breaks down. From another viewpoint, there's nothing inside except information encoded on the boundary. From a quantum mechanical viewpoint, the interior exists in superposition, until observed. From a holographic viewpoint, the interior is equivalent to surface patterns. All of these answers are correct, all of them are incomplete. The question itself reveals the limitations of human intuition. When confronted with the deepest mysteries of physics, we expect reality to have a single definite description. But reality at its most fundamental level might be more like a quantum superposition of descriptions, each equally valid, each equally limited. What black holes teach us is that the universe is not just stranger than we imagine, it's stranger than we can imagine, and perhaps that's the most valuable lesson of all, that reality exceeds our ability to comprehend it completely, that there will always be mysteries, that push the boundaries of human understanding, that the cosmos will always have surprises in store for minds brave enough to peer into the darkness and ask what's really there. The darkness, it turns out, is not empty at all. It's full of information, full of possibilities, full of realities we're only beginning to glimpse. And that makes the universe not a lonely cold place of destruction, but a cosmic information processing system of unimaginable complexity and beauty. Even in the heart of a black hole, even at the edge of destruction, the universe finds ways to preserve, to process, to remember, to dream. And maybe in some strange quantum mechanical sense, that's exactly what we're doing right now.